Good afternoon. I'm Mike Solomon, the Interim Dean of the Graduate School. Welcome, and thank you for coming to this afternoon's event. This is an event that celebrates what we hold at highest esteem at the University of Michigan. As one of the finest research universities in the world, we pride ourselves on our faculty, their research, their teaching, and their place in the world of scholars. So it's fitting that we are here today to honor Professor of Mathematics, Robert Griess, Jr. He joined the University of Michigan faculty in 1971 after earning a PhD from the University of Chicago. Dr. Griess is one of the world's foremost mathematicians working on finite simple groups and vertex algebra theory. Groups are fundamental in mathematics and offer a powerful way to explore many problems, including those involving symmetry in physics and chemistry. Dr. Griess contributed substantially to the classification of finite simple groups. The classification required finding all the sporadic groups and proving there were no others. He is renowned for co-discovering and constructing mathematics' largest sporadic simple group, called the monster, because of the large number of elements involved at 54 digits. This feat, accomplished without using computers, has provided the foundation for new theories involving finite simple groups, arithmetic geometry, and mathematical physics. It has had profound, far-reaching consequences in many mathematical areas, including string theory and number theory. In announcing the discovery, the National Science Foundation said, "A scientist has taken a major step toward the solution of a long-standing problem in mathematics, an accomplishment that involved a structure with so many elements that he had to develop new ways of doing the computations, because even high-speed computers could have taken many years of full-time continuous operation to do the job." This is only a small part of Dr. Griess's research, but is one of the most famous achievements of any mathematician. He became increasingly involved in discrete aspects of Lie theory, vertex operator algebras, and lattices. His 2011 book, An Introduction to Groups and Lattices, Finite Groups, and Positive Definite Rational Lattices, offers a fresh introduction to the subject. In addition, he has published more than 89 articles in leading journals. His work has been recognized at the highest levels of his profession. He was a Guggenheim Fellow and an invited speaker at the International Congress of Mathematicians. He was elected to the American Academy of Arts and Sciences in 2007. The American Mathematical Society awarded him the Leroy P. Steele Prize for seminal contributions to research, one of the highest honors the Society bestows. In addition to his extraordinary research, Dr. Griess is a meticulous teacher who expects a great deal from his students. Throughout his career, he has been exceptionally attentive to educational issues. With a colleague, he developed the department's guidelines for PhD students and made pivotal contributions in setting up the department's initial use of computers. He established a new course, Advanced Linear Algebra, that provides an introduction to advanced topics to graduate students in applied mathematics, computer science, engineering, economics, and statistics. Dr. Griess is strongly committed to diversity. For 15 years, he ran the King Chavez Park's College Day Visitation Program in the mathematics department that brought to campus underrepresented minority students from middle schools. In recognition of his commitment, the U of M awarded him the Harold Johnson Diversity Award in 2003. The Distinguished University Professorship at the University of Michigan honors all of these important accomplishments. Established by our Board of Regents in 1947, the professorships pay tribute to the exceptional scholarly and creative achievements, superior teaching and mentoring, impressive record of service, and national and international reputation of our faculty. Dr. Griess has requested that his professorship be named in honor of his thesis advisor, award-winning mathematician John Griggs Thompson, who made critical breakthroughs in finite group theory and the classification of finite simple groups. Dr. Griess's lecture today is titled The Sporadic Simple Groups, 26 Characters in Search of an Oracle. Friends and colleagues, please join me in welcoming the John Griggs Thompson Distinguished University Professor, Professor Robert L. Griess, Jr.
Okay. Am I audible? Yes? Good. Okay, thank you. And I hope my computer works now. Wake up. There we go. Yes, good. And I'm going to be talking about scientific things, so there'll be technicalities here and there. I'll try to keep them brief. But the story of finite simple groups, besides being a hard mathematical challenge, is also like a detective story. You find one thing and then another, try to guess what's happening. And I'm going to sketch a little bit of the history so you can see all the drama that happened and why I got so interested in working in this field. So, but now I mentioned that my two mathematical ancestors, I had a collegiate professorship named after Richard D. Brower, who was a professor at University of Michigan from 1948 to 1952. And he was quite a very big international star in the area of algebra, and including a lot of important work in finite simple groups. Brower died in 1977. I think he was born in 1900. John Thompson is from a younger generation. He won a Fields Medal in 1970 for a series of powerful works in finite simple group theory. He and Walter Feit proved groups of odd order are solvable. And his work on N groups, I won't define that for you, but it's one of the early classifications of finite simple groups. Okay, now let's see if I can find. Okay, there's Richard Brower. He was president of the AMS around 1960. I think that's when the photo was taken. John Thompson around 1970. That's when I knew him as a graduate student. And here he is now, just a few years ago. Okay, so I'll remind people, mathematicians, what a group is. It's a set with an associative multiplication, an identity, and an inverse for every element. And I'll give two examples. If you've got a set, you can imagine permutations of the elements of that set. The set of all permutations forms a group, and the multiplication in that group is just the composition of functions. So if you have two permutations, you first perform one, follow that by performing the other. That resulting permutation is the product. And the second example comes from matrix theory. If you have a group of invertible matrices, the product of the matrix product gives you the group law. A simple group is a group which has more than one element, and in which the only normal subgroups are one and the whole group. And a normal subgroup is something that gives you a quotient structure. If you have a group, I'm pointing to my screen, that's not very intuitive. Okay. If you have a group and a normal subgroup, you can kind of collapse by the normal subgroup and get a quotient group. Okay, if that's not possible in such a G is called simple. Any finite group has a series of that sort where the quotients, as you go all the way down, are simple groups. And so we can understand a lot of things about finite groups by having very complete knowledge about the finite simple groups. So that motivates the classification of finite simple groups. Okay, now by the early 1960s, here's what we knew. Cyclic groups of prime order, these are the only commutative groups that are simple. Groups of Lie type over finite fields. There are about 17 families. And Chevalier essentially gave the main idea for transferring, let's say, a Lie group, a matrix group over the real or complex numbers to a group over any field. So think of the integers mod p, for example, a finite field, and the set of all n by n matrices over a finite field will just be a finite set. So the group you would get would be a finite group. Okay, so Chevalier groups will give you things that are that look like the projective special linear group, the projective orthogonal group, and so forth. And then there are twisted variations that give you the unitary group, things involving field automorphisms. And then there is a group of things that are kind of hard to classify. 5 groups discovered by Émile Mathieu in the 1860s. M11, M12, M22, M23, M24. And the subscript indicates that M sub n is a subgroup of the symmetric group of degree n. The smallest one has order 7920, and it acts on 11 points. M24 is five-fold transitive. That's a rather amazing property. If you have two sequences of 5 points, then there is an element in that group that takes the first member of one sequence to the first member of the other, and then the second, and then the third. Aside from the symmetric and the alternating groups, there just aren't any other examples of that besides M24 and M12. Okay, now, the word sporadic comes from the classic book of Burnside. I've forgotten whether it's in both editions. The second edition is a little different from the first because it recognizes the value of group characters, but I think that's the main difference. So he thought those 5 Matthew groups were really quite interesting, and he called them sporadic. So the term now means, in modern age, a finite simple group that does not belong to one of the naturally defined infinite families. Okay. Now, people got to work, and I'll say some details about this in a few moments. In the 1950s, Richard Brouwer started with an idea that I'll describe in a moment. People got on board, and there was a tremendous crew of people working. The classification of finite simple groups comes to about 10,000 journal pages, at least the first version. And it's been shrunk down to perhaps a half of that at this time. And it's really extremely hard. The list of finite simple groups in categories A and B are the same, but we found more sporadic groups. There are 26. The last was discovered in 1975. That's 42 years ago, and we believe the classification is solid at this point. So that is the number, 26. Okay. Now I'm going to touch on just a few highlights, and I'm going to mention University of Michigan faculty who participated in this great adventure. Okay, Donald Higman. I meant Richard Brouwer is one of them, sorry. Donald Higman, Jack McLaughlin. These colleagues I spent many years with, and they died. Jack died, I think, 1999. I'm not sure of the year. And Don Higman died in 2006. And there I am. I'm not dead yet, so just wait. Yes, sorry, I meant to mention Brouwer's idea. He announced in 1954 at the International Congress that the way to try to classify finite simple groups was to look at centralizers of involutions. Now, an involution is an element of order 2. If you apply the transformation twice, you get the identity. And the centralizer is the set of group elements that commute with it. Okay, let me give you an example with matrices. Take 3 by 3 matrices over a finite field of characteristic not 2, and take that diagonal matrix, and you think about the matrices that commute with it, and they look like the matrix just below, C and A down the diagonal. A is a 2 by 2 block, an invertible matrix, and the condition is C times determinant of A equals 1. And we have to take this mod scalars. I'm looking in the projective group. Okay. And Brouwer proved that if you've got a finite simple groups with an involution as in that group that I just described, then the finite simple group must be PSL3Q, which was the source of the example, except when Q equals 3. There's a branch in the analysis that leads to another case, which turns out to be the Matthew group M11. So if you'd never met the Matthew groups before, you would meet it this way. Okay. Now, this strategy of using the characterization by centralizer of involution was carried out literally to a point, but then it had to be modified and made a little bit more selective. So I can't give details. Now, the deluge, yes. Centralizer of an involution problem. Well, one of the bottom, I think the third line from the bottom, A cyclic group of order 2, direct product, the simple group of order 60, was proposed as the centralizer of an involution. And surprise, there it turns out to be a finite simple group that no one had known about. It was found by Zvonimir Yanko, order 175560, and there is that number factorized. And it was really quite stunning that this would happen. Now, it was constructed by a computer, and John Cannon did this by taking these two matrices over the integers mod 11 and proving that they generated a group of order 175560 contained in G2 over the field of 11 elements. So that was really something amazing. So there's kind of a connection with groups of Lie type, but in characteristic 11. Okay, now people didn't know what to make of that. So here's one idea. Think of the order of the general linear group, GLN, over the field of Q elements. Q is a prime power. And the order is that number. It looks like a polynomial expression. Well, this number, the number of elements in this new group, has order 175560, and it can be written that way as a polynomial expression in 11. So people thought, for at least a couple of hours or maybe a few weeks, there could be a series of groups over fields of characteristic 11. Q is a power of 11, but it turned out not to be the case. Now here's something that's kind of fun. That number factorizes as the product of 4 consecutive numbers and the product of 3 consecutive numbers. Now, I don't think anyone's ever done anything like that, but certainly provocative. And people just didn't know what to make of this. Now, around 1968 to 1969, there was a tremendous burst of discoveries. And some of these were found by centralizer of involution problems of the kind I described, but others came from different theories. Our former colleague, Donald Higman, developed the theory of rank 3 groups. You can think of that as a group acting on a graph. It's transitive in all the vertices, and each vertex is connected to some, but not all of the other vertices. So that's one property of rank 3 groups. And then there's sort of a number theoretic object, the Leech lattice. This Leech lattice has been mentioned many times since it was discovered in 1965. It's quite a fascinating thing. It has a huge group of isometries, a finite group, which I'll tell you about. And it also gives the densest packing of spheres in 24 dimensions. And that's a recent theorem. Okay. So now a cluster of sporadic groups were found by the Higman theory of rank 3 graphs. And Jack McLaughlin just took the Higman theory and said, well, where can I find examples of groups that would satisfy these numerical conditions? And he thought of one, and very quickly he discovered a new sporadic groups. So Higman's theory was really quite useful. A cluster of groups were found by a centralizer of involution studies. Bairnfisher found 3 groups that are connected to the Matthew groups M22, M23, M24, hence the subscripts 22, 23, 24. They were found by special kinds of finite geometries. And I'll mention again the Leech lattice. It's an even positive definite integral lattice in dimension 24. The fundamental domain has volume 1. And it's the only lattice in which the minimum self-inner product of a vector is 4. The other lattices have minimum 2. In fact, they contain large root lattices of rank 24. And when Conway found this Leech lattice, he looked inside and he rediscovered the Matthew groups and the groups discovered perhaps a few months earlier of Higman, Sims, McLaughlin, Suzuki, and Hall-Yanko. So that was, if he'd been a little faster, he would have had a greater number of groups to his credit. Okay, well, this is a tremendous amount of information for people to deal with, and there was really quite a stir. Don Higman made a funny remark that I want to pass along to you. There was a meeting in Urbana, Illinois, finite group theory meeting in 1968. I was a graduate student grunt at that time, so I didn't get to go. But this story was reported back to me. Jacques Titz, who is an eminent theorist in group theory of many kinds, he says he thinks of the general linear group as the sun with all the other groups rotating around. And Donald Higman immediately said, one can go blind looking directly at the sun. So, meaning it's not just the classical ideas that have to be followed. So that was terrifically funny. Okay. So that last cluster brought us up to 19 groups, and then between 1970 and 1975, there were 7 additional groups found, and I will just mention one that I've been associated with, and that is the monster. It was discovered independently, almost the same weekend, in 2 different parts of the world. Bernd Fischer was in Bielefeld, and I was in Ann Arbor on my apartment on Pauline Boulevard. And we found evidence for a finite simple group. And evidence is considered good if the experts can't destroy it as a likely place to find another simple group. And this looked really good. So we had a putative simple group, and there were various arguments that were put together to get the order. It involves powers of 15 primes, and it's a 50 to 4-digit number. I used to write it out on the board when I lectured on this, but I'm not doing it now. Okay. Now, the monster, if it exists, has the property that if you look at subgroups and quotients of subgroups, you can pick out 20 of the 26 sporadic groups. So it's really kind of a master object that contains a great deal of the story of sporadic groups. But 6 are on the outside. They're pariahs, as I call them, and they need other theories to describe them. Okay. And when the monster was, evidence came up, it was so big, and it was just beyond what people thought could be done by computer. For example, there had been several constructions by computer. And even theoretical work, the numbers were just so big. And people also faced the possibility that there may be quite a few other groups much, much bigger than the monster out there, and why you should exhaust yourself working on something that isn't really indicated to be the most important thing was a good question. So there was a lot of hesitancy. Okay, 10 to the 54, how big is it? Well, if you go to your penny collection and put 44 pennies on the table, look at permutations. The number of permutations is 44 factorial. It's just a bit over 10 to the 54. If you take 9 by 9 matrices over the field of 5 elements, the invertible matrices, it's about 10 to the 56 of those. And if you want matrices of 0s and 1s, invertible, 14 by 14 matrices give you a group of order about 10 to the 58. Okay. Existence. Oh, I meant to show a picture of Bernd Fischer. I think this must be a recent picture. I haven't seen him for a while. So what I did I did some analysis and found that the smallest degree of a matrix representation would be 196883 by 196883. That's too big to put on a page. And so there is the idea of trying to build some structure on a vector space of that dimension, and there is some experimental work by Simon Norton that indicated there would be an algebra structure, a non-associative commutative algebra structure, and the action of the monster would be automorphisms of this special structure. So that was the extra rigidity in the matrix representation that I found very useful. So I defined an algebra of that dimension and a set of invertible linear transformations that preserve the algebra product and proved that those transformations generated a group that satisfied the hypotheses for the monster. Okay. Now, later I added one dimension to make an algebra with a unit. And you wonder why I didn't do that in the first place, and the reason is that there are many ways to do it. There wasn't a unique way. But later there turned out to be a natural candidate. Okay. So here's the space. You can see B in boldface. It's a direct sum of three spaces. U is 300 dimensional. You can think of that as symmetric 24 by 24 matrices. V has dimension 98280. Think of it as pairs. Lambda inverse of shortest vectors in the Leech lattice. There are 196,560 of those. And W is a tensor product of a 24-dimensional space with a space of dimension 2 to the 12. These are all representations of a group called C that looks like 2 to the 1 plus 24, it's about 2/3 of the way down, extended upwards by Conway, the first Conway group. 2 to the 1 plus 24 is like a Heisenberg group over the field of two elements. It's called an extra special group. Okay, so I tried to imagine a group G of algebra automorphisms that was bigger than C. But there are a lot of parameters to choosing algebra structures. There were essentially 6 parameters. So I had to work in parallel, picking a sensible algebra structure and transformations that would preserve that algebra structure. And it was big and complicated. I had to blend all the notation and many relationships with subgroups of C and this imaginary extra element. So each time I had a candidate, it took me about a week to verify whether or not I had an algebra automorphism. It was really quite time-consuming. I was up working around the clock from about October 1979 to early January. Finally, I got one. And the story was I was on my first sabbatical from University of Michigan at the Institute for Advanced Study. And once I got hooked on this problem, I was working around the clock. It was really kind of intoxicating being so fanatical about this work. I did manage to watch Soupy Sales almost every day before going to lunch and to get the juices flowing. And the IAS is a good environment. They have great food, and it's very peaceful, good library. And I did get sort of a guardian angel there. Enrico Bombieri was interested in my work, and he was very friendly with me. And he once came by my office at 4 a.m. just to see that I was actually there. I told him that I was. And so we socialized quite a bit. And then I announced my proof by mail on January 14, 1980. And I think my best description of it was the heavens opened up and all the angels in heaven burst into song. That's how I felt. So, really. Now, what does this all mean? Well, you see, most simple groups, finite simple groups, are groups of Lie type. They're modeled on Lie algebra theory. So, and a lot of Lie algebra theory carries over to study of conjugacy classes, representation theory. But what do you do about these sporadic groups? There was a cluster of different themes that created them. Well, there were some interesting developments. The most striking one is a monstrous moonshine. There is a famous function in number theory called the elliptic modular function. And John Mackay noticed that the coefficient, it's called J of tau, 4 lines from the bottom. The coefficient 196884 is 1 plus 196883, and that's easy to check. And 196883 is that number that we believe was the dimension of the monster, an irreducible representation. Well, there are a lot of big numbers in mathematics. It's no surprise that two numbers would seem to be related for no particular reason. But when you continue to the next coefficient, 214,93760, that is also the sum of three dimensions of irreducible representations of the monster. And you keep going until you get tired of computing with such gigantic numbers, and it always seems to be true. This was an idea of Thompson, who suggested that there be a graded space, so that graded by the integers, so that the graded trace would be interesting. And at the identity, you would get the elliptic modular function. Conway and Norton said, yes, that really is true. And furthermore, the traces of elements of the monster gave you what are called Haupt-modulum, standard generating functions for genus zero function fields associated to discrete groups. And it's just too technical for me to go into. So here you've got classical 19th century number theory and late 20th century sporadic group theory. Suddenly, there's overpowering evidence that there's some big thing going on that displays these coincidences. Okay, now this was an idea that people tried to make work for other sporadic groups, especially those pariahs, the 6 groups that aren't in the monster. This was, there are some fractional results, but basically there's no direct generalization of it. Now, Andrew Ogg said, well, if you take the genus zero function fields at this level P, take the integer matrices A, B, C, D, so that the prime number P divides the lower left entry, C. That's connected to a quotient space of the upper half plane that has genus zero. What are those primes for which you get genus zero? And the answer is, it's those 15 primes. And he said, wait, those are the 15 primes that are in the order of the monster. Why should this be true? Well, he offered a bottle of Jack Daniels, so this is called the Jack Daniels bottle. It has not been explained, but there are some partial results about it that was published recently by Duncan and Ono. So if you're interested, have a look at that. Now, this is one of my favorites. Take this diagram. You've got numbers running around the bottom, 1A, 2A, and 3A. Forget the letters. Just look at the numbers for the moment. This is the Deakin diagram for the affine Lie algebra E8, or the extended Deakin diagram for E8. And these numbers, 2, 3, 4, 5, 6, 4, 2, and 3, are the coefficients of the highest root of E8. This is a purely Lie algebraic result. And John Mackay, who's a master of conjecture, said, well, look, there's a class of elements of order 2, a conjugacy class of involutions in the monster, with the property that when you take 2 of them, any 2 elements of order 2 in any group generate a dihedral group. What dihedral group do you get? In the case of the monster, the dihedral group has order twice one of these numbers, 1, 2, 3, 4, 5, 6, 4, 2, and 3. That's really just amazing. Why should that be true? Well, I actually put in some work. I had a collaborator, Ching-Hung Lam. I visit in Taiwan frequently. And we have some partial, it's a model of this. It's not really an explanation, but it's not just a leap across space without seeing what you're cruising over. There are some well-known theories underneath all the steps. Okay, vertex algebras. These are infinite dimensional operators that came up in physics. And as far as I know, they go back at least to the theory of the dual resonance model in the mid-70s. And they have something to do with the life of a particle. And I'm not qualified to explain this in any detail. These were modified by Lie algebraists to give representations of infinite dimensional Lie algebras, especially affine Lie algebras. And they were further modified by Frankel, Lepowski, and Merman to create a graded space where this idea of Thompson is realized, namely the traces of elements in that graded space give you these Hauptmoduln for the genus zero function fields. And this object is also, it's a vertex operator algebra, and it's called the Moonshine VOA. And this has been, people have tried to generalize this in certain ways, and there has been some small successes, but not a big one. And I also mentioned that in 2007, Ed Witten, a theoretical physicist, proposed some models involving 3D gravity. And these were models that were conjectured to be relevant. Only one was known to actually exist, and that was the Moonshine VOA. So, a bit about me. Do I get to talk about myself a bit? Oh, good. Okay. I was born in Savannah, Georgia at the end of World War II, and my parents took me back to Pittsburgh. We lived on the north side for my first 10 years. And I loved sitting on the porch watching things going on the street. And my first mission in life was to become a garbage man. And the reason is I love these guys. They came out, there was a truck, they all leaped off the corners, threw open a great burlap square on the street, took these cylindrical garbage cans, you see all the mathematical shapes here, and then they folded the corners, throw it over their shoulders, and then jumped back on the truck, dumped it out, and went on. I thought that was the greatest thing. So, well, time went on. 1957, I think I was about age 11, I accepted a job delivering newspapers. And a few days later, the headline said, "Russians win space race." What happened? Sputnik, right? Suddenly there was a mission to do science. So that propelled my enthusiasm for science. And I went on to, my parents moved to the suburbs. I also went to public schools there. In the city of Pittsburgh, they were racially integrated. I don't know whether they were integrated or not, but I didn't see any, saw only white people in the suburbs, in the schools. Went to the University of Chicago for college and graduate school, and then I came here, and I've been here for 46 years, I guess. Let me mention a few other things. Oops, no, not that. I like to do sketches, especially at dance and theater performances. This was at a play. I can fill 20 pages of a sketchbook. And this is a painting I did recently of a plaster bust I bought in China. Some more sketches. Dog sleeping in a park, Tainan. It's very hot in Tainan. And these are some Chinese co-workers playing cards. And it was kind of gloomy and dark, so I didn't feel like putting much color in this. Portrait. This is a recent self-portrait I did. Do I have another minute or two? Okay, good. I want to, where the heck is it? So, my buddy Peter Sparling was performing on Power Center in 2002, and he asked me if I would like to sketch. I'm in the lower left. You can't see me very well.
The story was about two people building a bridge. They were partners, and they lived in this space together. And at first they thought that they were building a bridge to the outside, because that's what couples do, they thought. But even with practice, they found themselves alone, time and again. Alone with each other. And then they found that the story they were telling was that they were building a bridge to each other and trying to figure out where that bridge, that is, the bridge of the two of them, where that bridge would finally go, where that bridge finally was. And as it turns out, it goes from the past, from kids' games, to flirtations, to riding and being ridden, to being companions. It leads from the line in the sandbox to the line we tell each other not to cross. It leads to the rest of your life, our lives, sleeping and awake, living and dying and living again. That's where it leads. We have a system.
Okay, thank you.
Interested in the connections that you talked about. In a number of points, I was, the relationship between one of the groups and infinite sphere, or sphere packing in Dimension 24, the coefficients in that polynomial representation you had. For someone outside the field, do you find when there's coincidences or connections like that, that they are typically worth tracking down? Are they usually telling you about something new, or are they just as often just coincidences?
Yeah, I think that's...
Hi, Bob. You had mentioned that in the introduction, I think your colleague did, that much of this work was done without computers. Could you talk a little bit about what might have happened had you been able to work the problem out or solve the problem with a computer?
Can you hear me? It's better. Okay. I guess my inclination would be to avoid using computers. But I was cautioned at that time that, for instance, if you try to describe the monster by permutations, you need at least 10 to the 20 symbols. And that was stretching the capacity of a computer to hold such a permutation and maybe multiply such permutations. So I was really put off. I didn't really think about it seriously because it was understood to be beyond the limits of computing. Yes.
Where we had learned a lot about iterating and driving your errors to zero, it's intriguing to me that you would describe it in such a visceral way as the heavens opening up. So I'm asking you to say a little bit more about that.
Oh, I was ecstatic. I was ecstatic. This was a problem that many people thought would never be solved. And I did it, and I did it without computers, and it seemed to open the door to a number of other things, which I'm only slightly qualified to talk about. So yeah, I was just absolutely delighted. It was a once in a lifetime event. I was absolutely thrilled, and words fail me. I was walking on clouds for days. Yeah, Lajen, yeah.
Yeah, I have a question. I mean, in the end, you show us some of your artwork. So I'm curious, have you tried to give some artistic way of describing the monster or some model to show how beautiful it is?
No, because I've talked to journalists and writers who want to talk about the monster in some way. They've got their own way. And I tried to suggest, something like 196883 dimensional space with 10 to the 54 dancers dancing around and things like this. They've got their own idea, so I can't, it's a personal thing. It's just personal.
We have time for one more question.
So the monster is the largest sporadic group, right? And when did people realize that, and what's the story?
Well, no one has the right to say that until the classification of finite simple groups is closed down. But the last sporadic was discovered in 1975. That's the fourth Yanko group. Yanko had 4 groups. It's pretty good haul for one person. A few years after that, people got the idea that the techniques were sort of closing down the classification. They were limiting the possibilities. So at that point, we were kind of guessing that was the end. But it was only, let's say in the early 80s, that there was a claim that the classification was done. And the claim was actually an overstatement, actually, because there were some gaps that had to be fixed. But it is held up. So I would consider it completed. So it was only maybe by the late 80s that I really began to believe that it was finished. It's fun to find a new sporadic group. It's a beautiful thing. It's like finding a Greek pot in your backyard or something like that.
Thank you for attending our lecture. I invite you now to attend a reception just right across the hall. And let's thank our distinguished university professor one more time.